You know, there are moments in physics when the universe decides to break its own rules, and right now we're watching one of those moments unfold in real time. I need to tell you about something that has every astronomer I know staying up late, staring at their telescopes, trying to understand what they're seeing. An object called 3I, Atlas, has just reappeared after vanishing behind the Sun, and I'm going to be honest with you, it's not behaving the way we expected. Let me paint you a picture. Imagine you're tracking something from another star system, something that has traveled through the cold darkness of interstellar space for millions, perhaps billions of years. You're watching it approach our Sun, getting closer and closer to that inferno of nuclear fusion that could vaporize almost anything. Then, at the most critical moment, you lose sight of it. Not because it disappeared, but because the very thing you're trying to study has moved so close to the brightest object in our sky that your telescopes are blinded. It's like trying to see a firefly next to a stadium floodlight. For weeks, maybe months, you wait, you calculate, you wonder if it survived. And then, one morning, it emerges on the other side, and you realize something profound has happened to it. That's where we are right now with 3I Atlas. This visitor from beyond our solar system, this wanderer that has seen star systems we can only dream about, has survived its close encounter with our Sun, and it has come back changed. When I first heard the observations coming in, I felt that familiar electricity run through me, the same feeling I had when we discovered the first interstellar object, Oumuamua. But this time, something is different. This time, we're watching an interstellar visitor transform before our eyes, and what it's showing us challenges everything we thought we understood about these cosmic travelers. The brightness has changed. The color has shifted. The tail, that beautiful streaming signature of dust and gas, looks nothing like it did before. And here's what's truly humbling. This isn't just academic observation. This is evidence of vulnerability. Comets aren't eternal. They're times-dying asterisk. Every time they swing past the Sun, they lose mass. They bleed away their volatiles, water, methane, carbon dioxide, into the vacuum of space. The coma expands, then dissipates. The tail stretches behind them like a wound that never closes. And we can measure this. We can track how much smaller they become with each orbit. Comet Halley, for instance, loses approximately 250 tons of material times per second, times when it's near the Sun. Think about that. In the time it takes you to watch this video, Halley, if it were at perihelion right now, would have shed thousands of tons of itself into space. That's not sustainable. Eventually, comets run out. They become what we call extinct comets, rocky husks with no volatiles left to boil away, no coma to form, no tail to stream behind them. They look, for all intents and purposes, like asteroids. In fact, we believe many asteroids' times are times extinct comets. They've exhausted their fuel, their fire, and now they drift silently, unrecognizable as the brilliant visitors they once were. It's a sobering thought. But there's another fate that awaits some comets, and it's even more dramatic. Fragmentation. Sometimes the stress of approaching the Sun, the thermal shock, the tidal forces, the sheer violence of outgassing becomes too much. The comet's nucleus, held together by nothing more than its own weak gravity and frozen ices, simply comes apart. It breaks. We've witnessed this firsthand. Comet Shoemaker-Levy 9 famously fragmented into more than 20 pieces before it slammed into Jupiter in 1994. Comet Linear disintegrated in the year 2000 as it approached the Sun, breaking into a cascade of smaller fragments that gradually faded from view. And then there's Comet Ison. In 2013, Ison was supposed to be the comet of the century. Astronomers predicted it would become brilliantly visible, perhaps even in daylight. The world watched as it plunged toward the Sun. But Ison didn't survive. It grazed too close. The Sun's heat was too intense. And as it rounded perihelion, it simply dissolved. Its tail stretched across millions of miles, a ghostly remnant of what it once was. Within weeks, there was nothing left to track. Ison became a cautionary tale, a reminder that even in space, survival is never guaranteed. But here's what fascinates me most. Comets don't just die, they transform. When a comet disintegrates, it doesn't vanish into nothingness. Its fragments disperse along its orbital path, creating debris streams that Earth passes through every single year. These streams become meteor showers, the Perseids, the Leonids, the Geminids. Each August, when you see those brilliant streaks of light painting the night sky, you're witnessing the afterlife of a comet. You're seeing the funeral pyre of something that died centuries, maybe millennia ago. Think about that for a moment. Those shooting stars you wish upon, they're the scattered ashes of ancient travelers. Comets that journeyed from the edge of our solar system, survived countless orbits, and finally succumbed to the sun's relentless pull. Their death gives us one of nature's most beautiful spectacles. This is the poetry hidden in physics. The mathematics of orbital decay becomes a light show. The tragedy of disintegration becomes wonder. Now, let's talk about what happens when a comet doesn't die gracefully, when it doesn't simply evaporate or break apart quietly in the void. Let's talk about impact. 66 million years ago, something fell from the sky. Most people know it as the asteroid that killed the dinosaurs, the Chicxulub impactor. But here's what many don't realize. In the grand scheme of things, comets and asteroids are siblings in destruction. Both are remnants of our solar system's formation. Both carry unimaginable kinetic energy, and both have repeatedly reshaped life on Earth. The difference? Comets hit harder. Because of their eccentric orbits, comets approach Earth at much higher velocities than asteroids. An asteroid might strike at 20 kilometers per second. Terrifying, yes, but a comet can hit at 70 kilometers per second. At those speeds, the kinetic energy isn't just doubled or tripled. Due to the physics of energy equations, it's magnified exponentially. A comet impact releases energies equivalent to billions of nuclear weapons detonating simultaneously. We've seen the evidence. In 1994, humanity watched in real time as comet Shoemaker-Levy 9 collided with Jupiter. The scars left on Jupiter's atmosphere were larger than Earth itself. Each impact site, a wound in the Jovian clouds, remained visible for months. If those fragments had struck our planet instead, each one would have triggered an extinction-level event. Every single one. And here's what keeps me awake at night. We're not talking about ancient history. We're talking about something that happened during my lifetime. During your time's lifetime, perhaps. CNN covered it. Scientists around the world watched through telescopes as world killer after world killer slammed into another planet in our cosmic neighborhood. Now, I want you to imagine something with me. Picture standing on a beach, watching the ocean. The waves roll in, steady and predictable. You feel safe. The pattern is familiar. But you don't see the tsunami building far offshore. You don't feel the earthquake that triggered it. The water suddenly recedes in eerie calm, and then the wall of water appears on the horizon. That's our relationship with comets. We see a beautiful night sky. We observe predictable patterns. Planets orbit. Stars shine. Everything seems orderly. But beyond Neptune, in the frigid darkness of the Oort cloud, trillions of these frozen time bombs drift in a vast spherical shell surrounding our solar system. They've been there since the birth of our planetary system 4.5 billion years ago. Occasionally, and we still don't fully understand all the mechanisms, something disturbs them, maybe a passing star, maybe the gravitational influence of the galactic tide, maybe something we haven't even identified yet. And when that happens, one of these ancient ice balls begins its long fall toward the inner solar system. Toward us. The journey might take millions of years. The comet doesn't care. Time means nothing to a frozen chunk of primordial matter. It just falls and accelerates. By the time we spot it, if we spot it, it might be moving at 40, 50, even 70 kilometers per second. At those speeds, the kinetic energy is almost incomprehensible. We're talking about velocities that make our fastest rockets look like toys. Now, let me put that velocity into perspective for you. Imagine standing on a beach, watching waves roll in. Each wave takes maybe 10, 15 seconds to reach you. You can see it coming. You can step back. You have time. Now imagine a wave moving at 70 kilometers per second. That wave would cross the entire United States coast to coast in less than a minute, from Los Angeles to New York in 58 seconds. That's the kind of speed we're dealing with. And we're not talking about water. We're talking about rock and metal and ice trillions upon trillions of tons of cosmic material compressed by billions of years of gravitational forces into something harder than steel, moving with the momentum of a runaway planet. At those velocities, it doesn't matter what it's made of. Physics takes over. The kinetic energy formula, you remember it from high school, right? 1/2 mass times velocity squared. That squared part is what should terrify you. Because when you double the speed, you don't double the energy, you quadruple it. An object moving at 70 kilometers per second carries 16 times more destructive power than the same object moving at 17.5 kilometers per second. 16 times, not a little more. Not twice as much. 16 times. And here's where it gets even more unsettling. The dinosaurs never saw it coming. They couldn't. They didn't have telescopes. They didn't have satellites or space agencies or early warning systems. They were simply living their lives, completely unaware that their entire world was about to end. But we do have those things. We have the technology, we have the mathematics, we have the computational power to track objects, calculate trajectories, predict impacts years or even decades in advance. We have everything we need to see it coming. Everything except enough time to do anything about it. Because seeing the bullet doesn't mean you can dodge it, especially when that bullet is the size of Manhattan, moving faster than anything humanity has ever built, and headed straight for the only home we've ever known. This is the paradox of modern astronomy. We've gained the knowledge that should protect us, but with it comes the terrifying awareness of just how vulnerable we actually are. And here's what keeps me awake at night. The universe doesn't care about our detection systems, our political summits, or our 5-year plans. It operates on timescales that mock our brief existence. A killer asteroid could have begun its death spiral toward Earth when dinosaurs still ruled the planet, locked in an orbit calculated by nothing but cold mathematics and gravity's pull. Right now, as you're watching this, there could be an object out there with Earth's name written all over it. Not metaphorically. I mean, its trajectory has been determined for millions of years, and that trajectory ends here, with us. The only question is when. Let me paint you a picture that will fundamentally change how you see the night sky. Every single night, approximately 100 tons of space debris enters Earth's atmosphere. Most of it burns up harmlessly, creating the shooting stars we naively wish upon. But here's the unsettling truth. Size matters exponentially. Those harmless particles are typically smaller than a grain of sand. Scale that up to the size of a car, and you've got something that can level a city block. Scale it to the size of a football field, and you're looking at a regional catastrophe. Now imagine something the size of a mountain, moving at 70,000 miles per hour. The physics alone should terrify you. At those velocities, it doesn't matter if an asteroid is made of solid iron or loosely packed rubble. The kinetic energy is so immense that the distinction becomes academic. We're talking about impacts that release energy equivalent to millions of nuclear weapons detonating simultaneously. The shock wave alone would flatten everything within hundreds of miles. The thermal pulse would ignite wildfires across continents. And then comes the real killer, the one that ended the dinosaurs, the impact winter. Trillions of tons of debris ejected into the stratosphere, blocking out the sun for years. Photosynthesis stops. The food chain collapses from the bottom up. It's not the impact that kills most life on Earth. It's the darkness that follows. But here's where it gets even more disturbing. We've identified the big ones, mostly. The planet killers that would end civilization as we know it. Those we're watching, it's the smaller ones, the city killers, the regional devastators that slip through our nets. Objects a few hundred feet across that could appear with virtually no warning and strike a major metropolitan area. The sobering truth is that we've cataloged less than half of the near-Earth asteroids larger than 140 meters. Less than half. That's like a security guard who's only checked half the entrances to a building and declaring it secure. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 meters across. Nobody saw it coming. Not a single telescope, not one detection system picked it up before it entered our atmosphere. And when it did, when it exploded with the force of 30 Hiroshima bombs, it injured over 1,500 people and damaged thousands of buildings. Now imagine something 10 times that size, 20 times, a 200-meter asteroid striking New York, London, Tokyo, Mumbai. We're not talking about a local disaster anymore. We're talking about millions of casualties, economic collapse that would ripple across continents, infrastructure damage that would take decades to repair. But here's what keeps me up at night more than anything else: the complacency. Because we haven't experienced a major impact in recorded history, we treat it like a theoretical problem. We fund asteroid detection programs at a fraction of what we spend on preventing threats we face every day. NASA's planetary defense budget, it's roughly the cost of a single major Hollywood blockbuster. We'll spend $200 million to watch fictional asteroids destroy Earth on screen, but we hesitate to invest that same amount in actually preventing it from happening in reality. And yet, despite these limitations, we've made genuine progress. The DART mission in 2022 proved something extraordinary. We can actually change an asteroid's trajectory. We can punch a cosmic bullet with a cosmic fist and alter its path through space. When that refrigerator-sized spacecraft slammed into the asteroid Dimorphos, it changed the asteroid's orbit by 33 minutes. 33 minutes might not sound like much, but in orbital mechanics, that's enormous. Given enough warning time, that kind of deflection could be the difference between an asteroid hitting Earth and sailing harmlessly past us. But here's the problem with kinetic impactors. They require time, years of warning time actually. You need to detect the asteroid early enough that a small change in its velocity translates to a big miss when it reaches Earth's orbit. Hit an asteroid 10 years before impact? You might only need to change its speed by a few millimeters per second. Wait until it's 6 months out? You'd need to change its trajectory so dramatically that a kinetic impactor might not be enough. This is why early detection isn't just important, it's everything. It's the difference between having options and having none. And this brings us to the second method in our planetary defense toolkit, the gravity tractor. Now this one sounds like science fiction, but the physics is beautifully elegant. Instead of hitting the asteroid, you park a spacecraft near it, just hovering alongside for months or even years. The spacecraft's tiny gravitational pull, and I mean tiny, like the weight of a car, slowly tugs the asteroid off course. Think of it like this. Imagine you're trying to move a cruise ship with a canoe. Sounds impossible, right? But if you had years to do it, and you could push consistently in one direction, you'd eventually change that ship's course. The gravity tractor works on the same principle. Time and patience can accomplish what brute force cannot. The advantage here is precision. Unlike a kinetic impactor, which is essentially a controlled crash with some uncertainty in the outcome, a gravity tractor gives you fine control. You can adjust your position, change the force, and steer the asteroid exactly where you want it to go. It's like the difference between hitting a billiard ball with a cue stick and using your hands to carefully roll it into the pocket. But gravity tractors have their own limitation. They're slow, painfully slow. You'd need decades of warning time to make this method work. For a large asteroid, you might need multiple spacecraft working in tandem, each contributing its tiny gravitational tug to the collective effort. But there's a fourth option that combines brute force with elegance, the kinetic impactor. This is essentially cosmic billiards played at interplanetary speeds. You send a spacecraft hurtling toward the asteroid at tremendous velocity, and when it strikes, it transfers its momentum to the target, nudging it off course. NASA's DART mission proved this concept works. In September 2022, a washing machine-sized spacecraft slammed into Dimorphos, a small moon orbiting the asteroid Didymos, at over 14,000 miles per hour. The collision wasn't about destroying anything, it was about changing velocity, and it worked. The impact altered Dimorphos' orbit by more than 30 minutes, far exceeding expectations. Think about what this means. We no longer have to theorize about deflecting asteroids. We've actually done it. We've demonstrated that humanity possesses the capability to alter the trajectory of a celestial object. It's a milestone that deserves more attention than it received. The beauty of kinetic impactors lies in their simplicity. You don't need exotic propulsion systems or nuclear warheads, just mass, velocity, and precise navigation. Hit the asteroid in the right spot at the right time, and physics does the rest. The earlier you strike, the smaller the required deflection, and the more time gravity has to amplify that tiny change into a complete miss. But timing remains everything. A kinetic impactor needs years of advance warning to be effective. Strike too late and you won't impart enough momentum to matter. The asteroid continues its death spiral toward Earth, and you've accomplished nothing except an expensive fireworks display. Which brings us to the nuclear option, and no, I don't mean blowing asteroids to smithereens like in the movies. That would be counterproductive, turning one large threat into thousands of smaller ones, each still carrying deadly momentum. Instead, you detonate a nuclear device near the asteroid's surface, vaporizing a portion of the rock. That vaporized material jets away from the surface, creating thrust that pushes the asteroid in the opposite direction. This isn't science fiction. It's been seriously studied by defense agencies and space organizations worldwide. A properly designed nuclear deflection system could work on short notice, weeks or months instead of years, and could handle larger asteroids that other methods can't budge. But here's the catch, and it's a big one. Nuclear deflection is a political and diplomatic nightmare. The Outer Space Treaty of 1967 prohibits the placement of nuclear weapons in space. Getting international consensus to launch a nuke toward an incoming asteroid, that's almost as difficult as the physics itself. I've sat in enough international conferences to know how these conversations go. Every nation wants assurances. Who controls the launch codes? Who verifies the trajectory? What happens if the mission fails and we've just armed a potential weapon in space? The paranoia is understandable, but it's also potentially fatal to our species. We need frameworks in place times before the crisis hits. Because when you're staring down an asteroid with 6 months to impact, there's no time to negotiate treaties or establish trust between rival nations. The decision-making process needs to be clear, transparent, and immediate. This brings us to an uncomfortable truth. Our greatest vulnerability isn't technological, it's political. We have the physics figured out. We understand orbital mechanics, explosive yields, and deflection trajectories. What we don't have is a unified planetary defense system with the authority to act. Think about that for a moment. We live on a planet divided into nearly 200 nations, each with their own agendas, their own suspicions, their own political calculations. Yet we face a threat that doesn't recognize borders or ideologies. An asteroid doesn't care about your GDP, your military might, or your seat at the UN Security Council. It targets everyone equally. The irony is breathtaking. We've achieved nuclear fusion, sent probes beyond our solar system, and decoded our own genetic blueprint. Yet we struggle to create the simple international cooperation needed to defend our home. It's like a family arguing over who should call the fire department while their house burns down around them. The irony cuts even deeper when you realize we already possess all the technology we need. We can track a golf ball-sized object hurtling through space at 17,000 miles per hour. We have rockets capable of reaching any point in our solar system. We understand the physics of orbital mechanics better than we understand the stock market. The technological barriers? They're practically non-existent compared to the political ones. Here's what frustrates me as a scientist. We waste precious time debating whether space exploration is worth funding, whether asteroid detection is a priority, whether we should invest in planetary defense. Meanwhile, asteroids don't care about our budget cycles or political divisions. They don't wait for consensus. They operate on the cold, indifferent laws of celestial mechanics, and those laws have no sympathy for species that can't get their act together. I've sat in enough international conferences to know what happens when you put world leaders in a room together. We can agree on nothing until catastrophe forces our hand. The COVID-19 pandemic was a perfect rehearsal for an asteroid threat, and we failed spectacularly. Borders closed, nations hoarded resources. Cooperation collapsed precisely when we needed it most. If a virus that took months to spread globally could fracture our international response so completely, what hope do we have against an asteroid that gives us 6 months warning? But here's what gives me hope, and you need to hear this. When push comes to shove, humans are capable of extraordinary things. Look at the International Space Station. Countries that were once bitter enemies now share a laboratory 250 miles above Earth. Russian cosmonauts and American astronauts drink coffee together while orbiting at 17,500 miles per hour. If we can cooperate there, in the most hostile environment imaginable, we can cooperate anywhere. The question isn't whether we can defend ourselves. The question is whether we will. Whether we'll prioritize the survival of our species over the petty squabbles that dominate our news cycles. Whether we'll invest in detection systems before we need them, not after. I've spent my career trying to popularize science to make these concepts accessible. But sometimes I wonder if I've conveyed the urgency clearly enough. This isn't abstract speculation. This is probabilistic certainty operating on a timeline that spans our children's lifetimes, our grandchildren's lifetimes. The Torino scale and the Palermo Technical Impact Hazard scale aren't academic exercises. They're quantifications of existential risk. When astronomers discover a new near-Earth object and calculate its impact probability, they're not playing with numbers. They're assessing the likelihood of civilization-ending events. Here's what keeps me up at night. We've only cataloged about 40% of potentially hazardous asteroids larger than 140 meters. That means 60% remain unknown, untracked, unmonitored. It's like knowing that 6 out of 10 loaded guns are pointed at Earth, but we can't see where they are. The funding disparity is obscene. NASA's planetary defense budget is roughly $150 million per year. For context, that's less than the production budget of a single Marvel movie. We spend more on fantasy superhero films than on preventing real-world catastrophes. This should infuriate you. It infuriates me. But anger without action is just noise. So what can we do? How do we translate concern into meaningful change? First, we need to complete the survey. The Near-Earth Object Surveyor mission, currently in development, will detect 90% of near-Earth objects larger than 140 meters within a decade of launch. It needs full funding and political support. Second, we need redundancy. Multiple detection systems, multiple deflection technologies, multiple contingency plans. We can't put all our eggs in one basket when the basket is planetary survival. Third, we need international cooperation that transcends politics. An asteroid doesn't care about borders, ideologies, or trade disputes. The response must be coordinated, global, and swift. And fourth, we need you. Public pressure drives political action. When citizens demand investment in planetary defense, governments listen. When voters make this a priority, it becomes policy. This is one of those rare issues where individual advocacy actually matters. Contact your representatives. Support organizations like the B612 Foundation and the Planetary Society. Make noise. Make this issue impossible to ignore. Because here's the truth. We are the first generation in human history with the knowledge and technology to prevent our own extinction from asteroid impact. And we may be the last generation with the opportunity to do so before it's too late. Think about that responsibility. Think about what it means. Every child playing in a park right now, every couple planning their future, every scientist working late in a laboratory, every artist creating beauty, every teacher shaping young minds, their existence, their dreams, their potential, all of it depends on decisions we make today about planetary defense. This isn't about fear. This is about love. Love for this incredible, improbable, beautiful world we've inherited. Love for the future we want to create. Love for the species that looked up at the stars and didn't just wonder, we reached out and touched them. I've spent my entire career studying the cosmos, peering into the deepest mysteries of space and time, and I can tell you with absolute certainty, consciousness like ours is rare. Civilizations that can understand the universe are precious beyond measure. The fact that we exist at all is a miracle that took 4 billion years of evolution to achieve. We will not let that miracle end because we were too distracted, too divided, or too indifferent to take action. The asteroids are coming. They always have been. They always will be. That's not a threat. It's simply the physics of our solar system. What has changed is that for the first time in Earth's history, one species has the power to do something about it. We can see them coming from millions of miles away. We can track their orbits with extraordinary precision. We can calculate impact probabilities decades in advance. And now, with missions like DART, we've proven we can change their trajectory. We have the knowledge. We have the technology. What we need now is the collective will to prioritize this existential challenge above the petty conflicts that occupy so much of our attention. Because in the end, when we look back at this moment in history, and I believe we will look back because I believe we will survive, we'll recognize it as a turning point. The moment when humanity stopped being a passive victim of cosmic roulette and became the active guardian of our own survival. The moment when we finally grew up as a species. And that's really what this is all about, isn't it? Growing up, maturing as a civilization. Every species, every civilization must face its existential moment. The moment when the universe tests whether you're worthy of continuing. For the dinosaurs, that test came in the form of a mountain-sized rock from space, and they failed not through any fault of their own, but because they lacked the tools, the intelligence, the technology to pass it. We have those tools. We have that intelligence. The question is, do we have the will? I think about my own children, my grandchildren, and I realize that this isn't an abstract problem. This is personal. Every one of us is connected to the future through the people we love, through the legacy we leave behind. When I look at a young child, I don't just see innocence and potential. I see someone who might live to see the 22nd century, who might witness humanity spreading across the solar system, who might look up at Mars and see city lights twinkling in the distance. But that future, that beautiful, expansive future, only happens if we take these threats seriously now, if we invest in planetary defense now, if we map every potentially hazardous asteroid now, if we develop the deflection technologies now, not in some far-off tomorrow when it might already be too late. And here's what gives me hope. We're already doing it. Not as fast as we should, not with as many resources as we need, but we're doing it. DART wasn't a fluke. It was a proof of concept, the first practical demonstration that we can change our cosmic destiny. NASA's NEO Surveyor, set to launch in the next few years, will revolutionize our ability to detect threats. The international community is slowly waking up to the fact that asteroid defense isn't science fiction, it's science necessity. But we need more. We need to treat planetary defense with the same seriousness we treat national defense. Because in a very real sense, it is the ultimate form of defense, defending not just a nation, not just a continent, but the entire human species, every living thing on this planet. Think about it this way. We spend hundreds of billions of dollars every year on military budgets around the world. We build aircraft carriers, stealth bombers, missile defense systems, all designed to protect us from threats that might never come. And I'm not saying that's wrong. National security matters. But here's the irony. All of those weapons, all of that technology, all of that military might, it's completely useless against an asteroid. You can't shoot down a mountain-sized rock with a fighter jet. You can't negotiate with a comet. You can't sanction an asteroid into changing course. The asteroid doesn't care about your politics, your borders, your ideologies. It doesn't care if you're American or Chinese or Russian or European. It treats everyone with perfect equality. It will wipe us all out without discrimination. So why then do we spend so little on the one threat that could literally end everything? It's a question that keeps me up at night, because the answer isn't rational, it's psychological. Asteroids feel abstract, distant, like something from a science fiction movie. Military threats feel immediate, even when they're not. But the truth is, we have the power to change this narrative. We have the technology, right now, today, to protect ourselves. We don't need to invent some miraculous new physics. We just need the will, the funding, and the international cooperation to make it happen. And there are signs that we're moving in the right direction. NASA's Planetary Defense Coordination Office is mapping near-Earth objects. The DART mission proved we can deflect asteroids. Countries are starting to talk about this as a global priority. But we need to accelerate. We need to treat this like the Manhattan Project or the Apollo program, a focused, well-funded international effort with a clear goal: ensure that humanity never suffers the fate of the dinosaurs. Because here's what gives me hope. Unlike the dinosaurs, we can see it coming. We have telescopes, we have computers, we have spacecraft. we have the one thing they didn't have: the ability to change our destiny. And that's not just theoretical, we're already doing it. In 2022, NASA deliberately crashed a spacecraft into an asteroid, not by accident, on purpose. The DART mission double asteroid redirection test slammed into a small moon called Dimorphos at over 14,000 miles per hour. And it worked. We changed its orbit. For the first time in 4.5 billion years of Earth's history, humanity proved we could nudge a space rock off course. Think about that. We took a chunk of the cosmos, older than any civilization, older than any species on Earth, and we moved it. Not with prayers, not with luck with physics, with engineering. With the collective genius of thousands of people who decided that extinction was not acceptable. This wasn't a movie. This was real. And the data we gathered? It's teaching us how to scale up, how to detect threats earlier, how to respond faster, how to turn science fiction into survival strategy. But here's the thing, that capability, that power to defend ourselves, it comes with responsibility, because the same rockets that could save us from an asteroid could also be used to destroy each other. The same AI that could predict asteroid trajectories could be weaponized. The same global cooperation needed to track near-Earth objects requires us to overcome nationalism, politics, and short-term thinking. We have the tools. The question is, do we have the wisdom? And that's where you come in. Not scientists alone, not governments alone, all of us. Because the future isn't written in the stars, it's written in the choices we make today. The investments we support, the leaders we choose, the priorities we set. Every time you look up at the night sky, remember, those points of light have been watching over Earth for billions of years. They've seen species rise and fall. They've seen worlds collide. And now, for the first time, they're watching a species that can watch back, a species that can calculate, predict, and prepare. We stand at a crossroads. One path leads to the fate of the dinosaurs' extinction by cosmic accident. The other leads to a future where humanity takes its place as a truly spacefaring civilization, capable of protecting not just ourselves, but the precious flame of consciousness itself.